Let us look at the very important Fischer-Tropsch process, reference number 402.3 in your workbook.
Is that the process used by Cecil?
Yes, Stephen, the process is used to prepare hydrocarbons like petrol and other useful organic compounds. This process includes the very important water-gas shift reaction, which is an excellent example of a reversible reaction or chemical equilibrium. The first step is to gasify coal in air and steam to produce the water-gas mixture consisting of carbon monoxide gas, hydrogen gas, carbon dioxide gas, and water in the gaseous phase. The reactant molecules, carbon monoxide and water, both in the gaseous phase at the synthesis temperature of 330 degrees Celsius, collide to produce activated complexes that can decompose to form the product molecules, carbon dioxide gas and hydrogen gas, in the forward reaction, which is exothermic. At the same time, however, the carbon dioxide molecules and hydrogen molecules collide to form activated complexes that can decompose to form the initial reactant molecules, carbon monoxide and water, in the reverse reaction, which is endothermic. A knowledge of the factors determining the extent to which the equilibrium can be shifted to the left to produce more carbon monoxide gas and less hydrogen gas at the new equilibrium. In other words, to obtain a high ratio of the concentration of carbon monoxide gas in mole per decimeter cubed to hydrogen gas also in mole per decimeter cubed, or to shift the equilibrium from left to right to produce more hydrogen gas and less carbon monoxide gas at the new equilibrium. In other words, to produce a low ratio of the concentration of carbon monoxide gas in mole per decimeter cubed to hydrogen gas in mole per decimeter cubed is of utmost importance to engineers who must control the ratio of the concentrations of these two important gases.
But why, sir? Why is it so important?
Stephen, the correct ratio of the concentrations of carbon monoxide gas to hydrogen gas is of great importance to obtain the highest possible yields of hydrocarbons in this last reaction taking place in the Kellogg plant. Let's take the example where N equals 6. 6 plus 2 is 8 molecules of carbon monoxide gas. Reacting with 2 times 6 is 12 plus 5 is 17 molecules of hydrogen gas to produce octane, which is part of petrol, together with other branched hydrocarbons, making up the octane value of petrol, and 8 molecules of water. Let us start the reaction with only water and carbon monoxide, both in the gaseous phase, present in a closed container. Since the concentrations in mole per decimeter cubed of the reactants will be high in the beginning, the rate of the forward reaction will also be high. But since the concentrations of the products will be very low in the beginning, the rate of the reverse reaction will be very low. As time goes on, the concentrations of the reactants will diminish, while the concentrations of the products will increase. This means that the rate of the forward reaction will decrease from that to that, while the rate of the reverse reaction will increase from that to that. Eventually, a stage is reached where the rate of the forward reaction becomes exactly equal to the rate of the reverse reaction, and we have a dynamic chemical equilibrium. This is a kind of a two-way traffic where just as many particles of the reactant are converted to product molecules per second as the number of particles of product that are changed to reactant molecules per second. These changes now only take place on a microscopic scale. On this graph, we plotted reaction rate as a function of time. The graph shows that the rate of the forward reaction, carbon monoxide plus water producing hydrogen plus carbon dioxide, diminishes, while the rate of the reverse reaction, hydrogen plus carbon dioxide producing carbon monoxide and water, increases until the rates become exactly equal after t seconds when equilibrium is established. There is only one major condition for equilibrium, and that is that the concentrations in mole per decimeter cubed of all reactants and products must remain constant. This implies that, in the case of gaseous reactants and or products, that the pressure will remain constant at equilibrium, and all physical macroscopic properties like color or pressure in the case of gases, or the conductivity in the case of ionic reactions, etc., must remain constant. What are the factors that scientists can control in order to shift the equilibrium as far as possible to the right, in order to obtain the highest possible yield? The factors are concentrations of reactants and products in mole per decimeter cubed and temperature. We can shift the equilibrium by either increasing or decreasing the concentration of a reactant or a product, or by increasing or decreasing the temperature of the reaction mixture. In other words, by 4 different ways. Le Chatelier's principle, reference number 402.4, can be applied to make qualitative predictions about the effect of a change in any of these factors, concentrations or temperature, on the reaction equilibrium. That means whether the equilibrium will shift to the right to produce a high yield of product, or to the left to produce a low concentration of product. What is Le Chatelier's principle? Le Chatelier's principle states that when a system which is in equilibrium is subject to a stress, that means if any of the factors, like concentrations or temperature, affecting equilibrium is changed, then the equilibrium will shift its equilibrium in a direction that will minimize the stress. Let us see how this principle can be applied to a few examples. In this test tube over here, we have a solution of ammonium thiocyanate. When I add this solution of iron 3 chloride, the following equilibrium is established. The iron 3 chloride dissociates in water to produce yellow iron 3 ions that we have over here, and the ammonium thiocyanate dissociates in water to produce the colorless thiocyanate ions that we have over here. The iron 3 ions combine with the thiocyanate ions to produce blood red iron thiocyanate complexes. When you apply Le Chatelier's principle, you will find it very useful to state your answer according to the following 4-step guide. The first step is to establish the stress imposed upon the system. This could either be an increase or a decrease in the concentration, or the pressure in the case of gases, or an increase or decrease in temperature. The second step is to determine in which direction the equilibrium is shifted. That means whether the equilibrium is shifted to the right or to the left. In the third place, we ask ourselves how the concentration or yield of the products is affected by this shift. And in the fourth step, we finally have to give an explanation of how the stress is relieved or the change minimized. When I add this concentrated iron 3 chloride solution to our equilibrium mixture in this test tube, I actually add iron 3 ions to the solution, which means that the overall concentration of iron 3 ions in mole per decimeter cubed will increase. Let us see what happens. Le Chatelier's principle explains our observation as follows. In the first place, we have to identify the stress imposed upon the system. In this case, our stress is an increased concentration in mole per decimeter cubed of the iron 3 ions. In the second place, we have to determine in which direction this increased iron 3 ion concentration will cause the equilibrium to shift. In this case, the equilibrium is shifted to the right, since, according to the collision theory, the rate of the forward reaction will exceed the rate of the reverse reaction immediately after addition of the concentrated iron 3 chloride solution, since the number of collisions per second between the iron 3 ions and the thiocyanate ions will be higher immediately after disturbing the equilibrium. And in the third place, we have to ask ourselves the question how the concentration or yield of the products is affected by this shift in equilibrium. In this case, the concentration in mole per decimeter cubed of the product, iron thiocyanate, will be higher than before the equilibrium was disturbed. And consequently, the reaction mixture will turn deeper red. And finally, we have to explain how this shift in equilibrium will relieve the stress imposed upon the system. By shifting the equilibrium from left to right, some of the added iron 3 ions are used up, and consequently, the concentration in mole per decimeter cubed of the iron 3 ions will be lowered. And bearing in mind that the original stress was an increased iron 3 ion concentration, our stress will be relieved or minimized. This graph here shows how the concentrations of the reactants and of the products are affected by a stress imposed upon the system. At the initial equilibrium, the concentrations of the reactants and of the product are constant, as you can see here. Immediately after addition of the concentrated iron 3 chloride solution, the concentration of the iron 3 ions in mole per decimeter cubed will suddenly increase to this value. And thereafter, the concentrations of both the reactants iron 3 ions and the thiocyanate ions will decrease as they are being used up to form the complex iron thiocyanate, and the concentration of the iron thiocyanate will also increase at the same time until the rates of the forward and reverse reactions once again become equal. At this new equilibrium, the concentrations of all reactants and products will once again be constant. Also at the new equilibrium, the concentration of the iron 3 ions will be less than immediately after addition of the concentrated iron 3 chloride solution. But the concentration of iron 3 ions will be higher than before the equilibrium was disturbed, while the concentration of thiocyanate ions will be less, and the concentration of the products will be more than before the equilibrium was disturbed. Adding a concentrated solution of potassium thiocyanate has exactly the same effect as adding a concentrated solution of iron 3 chloride. Let me show you. In this test tube, I have a solution of potassium thiocyanate, and over here we have the equilibrium mixture. If I add this solution to my reaction mixture, we can clearly see that the equilibrium is driven to the right. For a detailed explanation of this observation in terms of Le Chatelier's principle, refer to reference number 402.4.1 in your video workbook. We can also shift the equilibrium to the left by either reducing the concentration in mole per decimeter cubed of the iron 3 ions or of the thiocyanate ions. Let us see what happens if I add a solution of sodium phosphate to my equilibrium solution. It is clear that the equilibrium in this case was shifted far to the left, producing an extremely low concentration of the final product, iron thiocyanate, in mole per decimeter cubed at the new equilibrium. This equation shows how the iron 3 ions will combine with the phosphate ions to produce an insoluble precipitate of iron phosphate, which amounts to an irreversible removal of iron 3 ions from the solution for all practical purposes. Jason, can you tell us what stress is imposed upon the system in this case?
The decreased concentration of the iron 3 ions.
That's right, Jason. Now, Ira, tell us, how can the concentration of iron 3 ions be reduced?
So the phosphate ions remove the iron 3 ions from solution.
That's right. Okay, now if the concentration of iron 3 ions is reduced, Jason, can you tell me how it affects the equilibrium here?
The equilibrium shifts to the left.
Okay, if the equilibrium shifts to the left, Eric, can you tell me how this shift will affect the concentration of the products?
Yes, so the concentration of the products decreases.
Quite right. Okay, if the concentration of the products decreases, can you tell me how the stress is relieved, Jason?
When it shifts to the left, some of the iron 3 ions are replaced.
That's quite right. By shifting equilibrium to the left, the concentration of the iron 3 ions will have increased, and therefore the stress will be relieved. This graph here shows that immediately after the addition of the sodium phosphate solution, the iron 3 ion concentration is reduced to this value, and then the concentration will increase since the rate of the reverse reaction will exceed the rate of the forward reaction during this interval when the equilibrium is disturbed. At the same time, the concentration of the thiocyanate ions will increase, while the concentration of the iron thiocyanate ions will decrease until the rates of the forward and reverse reactions once again become equal and all concentrations of reactants and products become constant at the newly established equilibrium. For our second example of the application of Le Chatelier's principle, we first have to prepare some brown nitrogen dioxide gas by adding this powerful oxidizing agent, concentrated nitric acid, HNO3, to the reducing agent copper in this flask, and then we half fill our gas syringe with a brown gas and seal the end. This is the equation of the equilibrium established between the colorless dinitrogen tetroxide and the brown nitrogen dioxide, both in the gaseous phases. A sudden compression of the gas mixture causes an instantaneous darkening. And from my position, I can clearly see that the nitrogen dioxide gas concentration is diminishing because the equilibrium mixture is getting lighter brown. It is important to note that the first instantaneous darkening is not due to the formation of more of the brown nitrogen dioxide gas molecules, but it is simply because we compressed the gas mixture into a smaller space. The stress imposed upon the system is an increase in the concentrations of both the dinitrogen tetroxide and the nitrogen dioxide as a result of the increase in pressure. How is the equilibrium affected by this increase in pressure? The equilibrium is shifted to the left. Now, how will the shift to the left affect the equilibrium concentrations or yield of the products? In this case, the concentration in mole per decimeter cubed of the brown nitrogen dioxide gas is reduced and the equilibrium mixture will become lighter brown. We still have to explain how the stress is relieved. The balanced equation shows that in the reverse reaction, every 2 molecules of brown nitrogen dioxide gas is converted to 1 molecule of colorless dinitrogen tetroxide gas, producing fewer molecules in the same space, and therefore we will have fewer collisions per second per unit area against the walls of the container and the plunger, and consequently the pressure will drop and the stress will be relieved. If the plunger is suddenly withdrawn, the equilibrium mixture will become lighter brown, and from my position I can see how the equilibrium mixture is now gradually turning darker brown. For an explanation of this observation in terms of Le Chatelier's principle, refer to reference number 402.4.2 in your workbook. Let us see what happens if we raise the temperature and drop the temperature. Here we have 3 flasks filled with the dinitrogen tetroxide, nitrogen dioxide equilibrium mixtures. Let us see what happens if I place this flask in hot water and leave this one at room temperature and place this flask in ice water. It is quite clear that for this flask in the hot water, the equilibrium shifted to the right. And for the flask in cold water, the equilibrium shifted to the left. Let us consider the change in equilibrium in the case where we place the flask in the hot water. In this case, the stress was the increase in temperature, which caused the equilibrium to shift to the right, and that in turn caused the concentration of the products, nitrogen dioxide gas, to increase and to be higher at the new equilibrium, and the mixture turned darker brown. Now, how is this stress relieved in this case? This is the potential energy curve of the reaction. We can see that the forward reaction is endothermic, which is a reaction which absorbs heat. So, by shifting the equilibrium to the right, some of the added heat is used up, and consequently, the temperature will drop, and the stress will be relieved. What happens in the case where we place the flask in cold water? For a complete explanation in terms of Le Chatelier's principle, refer to reference number 402.4.3 in your workbook. For our third example in the application of Le Chatelier's principle to equilibrium, we look at the equilibrium between the complexes of cobalt. When we dissolve cobalt chloride in water, we obtain this red aqua complex of cobalt. But when we dissolve cobalt chloride in alcohol, we obtain this blue cobalt complex of alcohol. Let me show you. This here is the solution of cobalt chloride in water. And over here I have the solution of cobalt chloride in alcohol. When I add water dropwise to the solution in alcohol, I obtain this equilibrium solution where the blue chloride complex combines with water to produce the red aqua complex and chloride ions. Next, I want to divide my equilibrium mixture into two portions. When I now add a concentrated solution of hydrochloric acid to the one portion, the solution turns blue, which means the equilibrium shifts to the left. But when we add water to the same solution, the equilibrium is shifted to the right. If I take my second portion and heat it in a beaker of hot water, the solution turns blue, which means the equilibrium shifts to the left. And if I take the same equilibrium mixture and cool it in ice water, the solution turns red, which shows that the equilibrium was shifted to the right. For the explanation of all these observations in terms of Le Chatelier's principle, refer to reference number 402.4.4 in your video workbook. For our last example on the application of Le Chatelier's principle, we consider the dichromate-chromate equilibrium. We start off by making a solution of potassium chromate in water, and then I add hydrochloric acid to the solution to produce this equilibrium we have here, where the hydrogen ions combine with the yellow chromate ions to produce the orange dichromate ions and water. If we now add a concentrated solution of caustic soda or sodium hydroxide to our equilibrium mixture, we see that the equilibrium is driven to the right because the hydrogen ions there are being neutralized by the hydroxide ions of the caustic soda to form water. On the other hand, if I add concentrated hydrochloric acid to the equilibrium solution, the equilibrium is once again driven to the left to produce a higher concentration of the dichromate ion at the new equilibrium. For an explanation in terms of Le Chatelier's principle of these observations, refer to reference number 402.4.5 in your workbook. Also refer to reference number 402.4.6 for a detailed explanation of the application of Le Chatelier's principle to the very important Haber process used for the manufacturing of ammonia, which in turn is used to manufacture very important substances like fertilizers, explosives, etc. Le Chatelier's principle can also be used to make qualitative predictions on the solubility of a given solute in a given solvent. That is, whether an increase or a decrease in temperature or an increase or a decrease in concentration will shift the equilibrium to the right to increase the solubility or to the left to reduce the solubility. We first have to see what we mean by a solubility equilibrium. If I add this water to the excess of salt in this beaker and then stir my solution, I find that some of the salt remains undissolved. In the beginning here, we have that the rate of dissolution will exceed the rate of precipitation of these ions onto the crystal surface, because the concentration of the sodium ion and of the chloride ions in the beginning will be low, which means that the rate of the precipitation will be low. But as the concentrations of these ions build up, the rate of precipitation will also increase until the rate of dissolution becomes exactly equal to the rate of precipitation, and we have a dynamic solubility equilibrium. And the solution is now called saturated because it will be saturated with sodium ions and chloride ions, of which the concentrations will now remain constant. If I now take this saturated solution and decant it into a test tube to leave the undissolved solid behind, then this solution here will still be saturated with sodium and chloride ions. If I add any substance that will dissolve in water to produce either sodium cations or chloride anions, in other words, if I add ions which are common to those already present, then we get the solubility will be greatly reduced. Let us add concentrated hydrochloric acid, which contains chloride ions. See what happens. A large mass of sodium chloride is precipitated, which means the solubility is greatly reduced. The stress in this case is an increased concentration of the chloride ions, causing the equilibrium to shift to the left, and thereby the solubility is greatly reduced. And the concentrations of the sodium and chloride ions will be greatly reduced at the newly established equilibrium, and in this way the stress will be relieved. The solubility of a salt can also be increased by adding a reactant that will combine with one of the ions present to form so-called complex ions. When I add the silver nitrate in this test tube to sodium chloride, I get a white insoluble precipitate of silver chloride. This equation shows the solubility equilibrium between the undissolved silver chloride and the silver and chloride ions formed. The concentrations of these ions will be very low at equilibrium, since most of the silver chloride will remain undissolved since the solubility is so extremely low. But when I bubble ammonia gas through the equilibrium mixture or add ammonium hydroxide, which contains ammonia, we see that the solubility is greatly increased. The stress in this case is a reduced concentration of the silver ions, causing the equilibrium to shift to the right, and thereby the concentrations of the products, the silver ions and the chloride ions, is greatly increased. And in this way, the stress is relieved. We can therefore conclude that the addition of a common ion to a saturated solution will always reduce the solubility by driving the equilibrium to the left in the so-called common ion effect, while the addition of a complexing agent to produce so-called complex ions will always increase the solubility by driving the equilibrium to the right. For a study of the effect of temperature changes on solubility equilibrium of a solute, refer to reference number 402.4.7 in your workbook. Stop your videotape now to attend to worksheet 402.1 on the applications of Le Chatelier's principle to a number of equilibrium systems and other related questions. Stop your videotape now. Although Le Chatelier's principle helps us to make qualitative predictions about the direction in which a given equilibrium will shift when we change the concentrations or the temperature, it cannot determine the exact extent to which this shift will take place. In other words, it cannot determine the exact concentrations of the final products that we desire at the new equilibrium. For this purpose, we apply the law of chemical equilibrium, also called the law of mass action. Reference number 402.5 in your workbook. Let us see how the law of mass action is derived from first principles. Consider the equilibrium between the reactants hydrogen and iodine to produce the products hydrogen iodide, all in the gaseous phase. According to the collision theory, the rate of the forward reaction is equal to the specific rate constant for the forward reaction times the product of the concentrations of the reactants to give us equation 1. And the rate of the reverse reaction is equal to the specific rate constant for the reverse reaction times the product of the concentrations of the products, which means the concentration of hydrogen iodide is squared, giving equation 2. But at equilibrium, the rate of the forward reaction, equation 1, is exactly equal to the rate of the reverse reaction, equation 2. This means equation 1 equals equation 2, or K1 times the product of concentrations of the reactants is equal to K2 times the concentration of hydrogen iodide squared. If I take K2 to the left and these concentrations to the right by cross multiplication, I get this expression where the quotient of the two specific rate constants will give us a new constant, Kc, which is called the equilibrium constant. Consider the general equilibrium equation where A molecules of reactant A reacts with B molecules of reactant B to produce C molecules of product C and D molecules of product D. The law of mass action can then be formulated as follows. The product of the concentrations of the products C and D divided by the product of the concentrations of the reactants, each expressed in mole per decimeter cubed, and raised to the power equal to the coefficient in the balanced equation, A and B, C, D, will give us a constant, Kc, which is called the equilibrium constant. In homogeneous equilibria, all the reactants and products are in the same phase. But in heterogeneous equilibria, the reactants and products are not all in the same phase. Consider the equilibrium established when limestone or calcium carbonate is strongly heated in a closed container to produce the solid calcium oxide and the gas carbon dioxide. In this case, we therefore have a solid and a gas involved. When we write the expression for the apparent equilibrium constant, Kxnc, we get this expression. The concentration of the carbon dioxide gas can be changed by compressing it or by expanding it or by adding more carbon dioxide or taking carbon dioxide gas away from the container. But the concentrations of the calcium carbonate and the calcium oxide, the solids, cannot be changed by any of these methods. The concentration of a solid is only determined by its density at a given temperature. If, for example, we add more calcium carbonate to the reaction mixture, the concentration of calcium carbonate will not be changed because the particles will still be the same distances apart in the solid phase. This means the concentrations of calcium carbonate and of calcium oxide are constants. And if we transfer them across the equal sign and multiply these constants with the apparent equilibrium constant, we obtain the so-called real equilibrium constant, Kc, which in this case is only equal to the concentration of the carbon dioxide gas. A second example to emphasize the importance of taking the phase as specified by the equilibrium equation into account when we write the mass action equation is given here, where hydrogen gas reacts with sulfur to form hydrogen sulfide. When the equilibrium is established at 1000 degrees Celsius, the sulfur, which melts at 115 and boils at 440 degrees Celsius, will be in the gaseous phase. So the real equilibrium constant in this case is given by this expression, where all the concentrations are involved. But we know that sulfur melts at about 115 degrees Celsius. So if the equilibrium is established at 200 degrees Celsius, sulfur will be in the liquid phase. And since the concentration of a liquid is constant at a given temperature, the constant concentration of the sulfur is included in the real equilibrium constant. The simple rule applicable to heterogeneous equilibria is that solids and liquids are always omitted from the mass action equation. The concentrations of ions in solution and of gases, however, are variable within certain limits and therefore must always be included in the mass action equation.
But sir, what is the use of all of this?
Yes, so why is the equilibrium constant so important?
Equilibrium constants are of utmost importance to chemists and chemical engineers since it enables them to calculate equilibrium concentrations, and also it helps them to determine the conditions required to obtain maximum yields of a desired product. A large value of Kc means the equilibrium lies far to the right, with the reaction running almost to completion, and the product's concentrations will be high and the yield will be high.
Sir, but why is the equilibrium constant large for a high yield of product?
Let us answer Lisa's question by looking at this equilibrium. Sometimes textbooks show equilibria with different lengths of the arrows. This doesn't mean that the rate of the forward reaction is greater than that of the reverse reaction. They are still equal, but it simply means the equilibrium lies far to the right in this case. The equilibrium constant Kc, in this case, is the product of two numerator factors which are very large, divided by two denominator concentration factors which are small. Dividing a large product by a small product will give us a large value for Kc. Era, how would we then interpret a small value for Kc?
Oh, please help me, Lisa.
Figure it out yourself and please don't make your problems mine.
Okay, the equilibrium lies far to the left and the yield will be small.
You knew it all the time.
Yeah, I think so myself, Era. Again, the rate of the forward reaction is equal to the rate of the reverse reaction, but this long reverse arrow indicates that the equilibrium lies far to the left, and the equilibrium constant Kc will be small since we divide the product of two small concentrations by the product of two large concentrations in this case. The value of the equilibrium constant Kc is always a constant at a given temperature, but for every different temperature, Kc will have a different constant value that must be taken into account when we use the mass action equation. Let us see how the equilibrium constant Kc is applied to calculate equilibrium concentrations of a reaction by looking at the water-gas shift reaction used by Sasol. Say we place 0.1 mole of carbon monoxide gas and 0.1 mole of water in the gaseous phase and nothing else in a 1 cubic decimeter container at 330 degrees Celsius. The first step is always to write the proper balanced equation. The balancing coefficients in this balanced equation tells us that 1 mole of water will react with 1 mole of carbon monoxide gas to produce 1 mole of carbon dioxide and 1 mole of hydrogen gas. So, if the concentration of the hydrogen at equilibrium is x mole per decimeter cubed, then that of the carbon dioxide at equilibrium will also be x mole per cubic decimeter. And the concentrations of the reactants will be 0.1, the initial concentration, minus x for the water concentration, as well as for the carbon monoxide gas concentration. The next step is always to write the mass action equation. In this case, we have the concentrations of the products on top of the line as usual, and the concentrations of the reactants at the bottom. The equilibrium constant for this reaction at 330 degrees Celsius, as written from left to right, is 24.2. Substituting all values of concentrations in this mass action equation, we get this expression. If we take the square of x and the square of 0.1 minus x, we get this. And taking the square root on each side of the equation, we get 4.92 equals x divided by 0.1 minus x. Transferring this factor to the right and multiplying this by 4.92, we get this expression. Taking the 4.92 across, we get 5.92x. And dividing by 5.92, we get that the final equilibrium concentrations of the products, carbon dioxide gas, and of hydrogen gas will each be 0.083 mole per cubic decimeter, while the concentrations of the reactants at equilibrium of the carbon monoxide gas and the water gas will be equal, and both will be equal to the initial concentration of 0,1 minus x, which is 0,083, which means it works out to 0,017 mole per cubic decimeters. This is the concentration time curve for the same reaction. The concentrations of the reactants carbon monoxide and water decrease from 0,1 mole per decimeter cubed to its final equilibrium value, which remains constant at 0,017 mole per decimeter cubed, while at the same time the concentrations of the products, carbon dioxide gas and hydrogen gas, increase from 0 to its equilibrium value, where it remains constant at 0,083 mole per cubic decimeter.
But sir, can we only get equilibrium if we start with carbon monoxide and water?
Can't we also start with carbon dioxide and hydrogen?
Yes, it can be done. Any equilibrium can be approached from either side, starting only with the reactants in the container or starting only with the products in the container. If we start with 0,1 mole of carbon dioxide gas and 0,1 mole of hydrogen gas in a 1 cubic decimeter container at 330 degrees Celsius, the same final equilibrium concentrations are attained. The concentrations of the carbon dioxide gas and of the hydrogen will diminish from 0,1 mole per cubic decimeter to its constant equilibrium value of 0,083 mole per cubic decimeter as before, while at the same time the concentrations of carbon monoxide and of water will increase from 0 to the same final constant equilibrium value of 0,017 mole per cubic decimeter. Refer to your video workbook, reference number 402.5.1 on a detailed calculation of the equilibrium concentrations obtained when the water-gas shift equilibrium is approached from the product side. Also refer to other examples mentioned there in the workbook on the application of the mass action equation. I want you also to refer to reference number 402.5.2 on the effects of a catalyst on equilibrium. Stop your videotape now to attend to worksheet 402.2 on the applications of the mass action equation on equilibria.